The majority of the IoT tasks are related to time, whether it's a communication, interfacing, or regular scheduled work. The Arduino framework provides developers with an infinite loop function that works as a single pass of a device working cycle. It is possible to extend the code with asynchronous background tasks management, such as the free real-time operating system. But this technique is beyond the basic scenarios that we represent in this tutorial. A very basic concept presents a blocking execution of the loop function using a delay function to stop the execution of the program flow for a specified amount of time. This code is a kind of hello world example that flashes a built-in LED every 2 seconds. While this approach is simple and suitable for elementary tasks, it is very inefficient in terms of code flexibility and energy consumption. A non-blocking solution is to measure the time passed between the task was last executed using the millis function or an equivalent one that returns the time passed since the last MCU reboot. This requires checking in the loop function whether the conditions to execute particular tasks have been met. It also requires the last execution time and delay specified for every task. Here is a sample code that flashes the built-in LED and the corresponding algorithm. Many IoT microcontrollers have special features, such as sleeping modes, which hold program execution for a predefined time or unless an external trigger occurs. This can be used for periodic, time-based activities such as sensor networking devices that wake up, take the measurement, send it, and then fall asleep. This model is energy efficient and enables devices to save energy, which is particularly important in constrained, low-powered sensor devices. Obviously, this requires an energy-efficient hardware design to save energy not only in the context of the microcontroller, but also in other components such as sensors, user interface devices, actuators, communications modules, and so on. Introducing the software implementation of the sleep mode brings significant energy effectiveness. For example, a typical ESP32 chip using a Wi-Fi connection consumes about up to 250 milliamperes of current, while in the deep sleep mode it's only 10 microamperes.